Hi, my name is Senja Boom and I currently work at Stedin. I recently finished my master's in sustainable energy technology from TU Delft because since I was young I've known that my passion is the energy transition because I want to do my part for this world. I soon discovered that the biggest challenge in the energy transition isn't in producing energy but in storing and transporting energy, which is why I focused on large-scale energy storage in my thesis, or more specifically on power to X to power, which is the subject of this lecture. These are the learning objectives today. What is power to X to power and why do we need it? What would a power to X to power system look like when connected to a Dutch wind park? And what are the challenges in power to X to power implementation? Those are the subjects we will cover today, starting with the need for power to X to power. A fully sustainable energy system can only function with large-scale energy storage. For the Netherlands, it's been predicted by TNO that we will need 100 terawatt-hour of energy storage by 2030. Large-scale energy storage systems do already exist. 80% of the world's energy storage is made up by pumped hydro electrical storage, PHES, which uses the height difference in water levels to store energy. The challenge for PHES is that you need large volume basins with large height differences, which are not available everywhere. In the Netherlands, for example, we don't have the capacities to store energy in pumped hydro energy storage. This is really too bad because this technology is really cheap and really efficient. Another alternative is compressed air energy storage. In order to efficiently store large volumes of compressed air, we need natural salt caverns. Unfortunately, those are not widely available either. The potential storage capacity in the Netherlands, for example, is only half a terawatt hour. This technology is slightly more expensive, but still affordable, and the round-trip efficiency is also acceptable. Since neither of these technologies can provide sufficient storage capacity, we will look at this final option, power to X to power. By storing gaseous fuels in the caverns mentioned before, we can increase the available storage capacity immensely. The available capacity in the Netherlands is way more than the 100 terawatt hours we need, which means we may absolutely need this technology. The levelized cost, however, is high and round-trip efficiency is rather low. So let's take a closer look at this technology. Now, what is power to power exactly? You start with excess electricity, and with that electricity you produce any type of molecule, X. Those molecules are now the energy carriers that you can store and transport. When you need electricity again, you use a fuel cell or turbine to produce power again, which you can feed back into the grid. There are many types of molecules that can be used to store energy. Most of them contain hydrogen atoms because they are light, widely available, and make energy-rich bonds. In my thesis, I selected the 3 most promising energy carriers to focus on, which are hydrogen, methane, and ammonia. So let us take the case of the Netherlands and look at the systems needed to store energy in molecules. The first energy carrier is hydrogen. I have taken the case of this 1 gigawatt wind park in the Netherlands, which produces power that is transported through DC power lines all the way to a grid connection point, which is the red dot on the screen you see. In this spot, most power will be fed to the grid directly, with minimal conversion losses. Only excess electricity will be converted to hydrogen using an electrolyzer. The electrolyzer will use the power and purified water to produce hydrogen. The hydrogen is transported through the hydrogen pipelines to the nearest suitable salt caverns and stored in the location marked by the green dot. Then when we need the power, we can transport the hydrogen back to the grid connection point and use a fuel cell to create electricity again. The next technology adds an additional step after the production of hydrogen. The energy carrier we'll be discussing now is ammonia. I consider the same wind park and the same power lines to the same grid connection point. In order to produce ammonia, you first need to produce hydrogen, the same way we discussed before, and you need nitrogen, which you can relatively easily capture from air. The hydrogen and ammonia are then fed into a Haber-Bosch reactor, which under high temperature, pressure, and catalysts produces ammonia. The difference here is that we can store ammonia in tanks, because ammonia can relatively easily be stored as a liquid through cooling and compression. This considerably increases the volumetric energy density. Regeneration back to power can be done with direct ammonia fuel cells. The final energy carrier I want to discuss here is methane. Again, it's the same wind park with the power line and the grid connection point, and at this grid connection point we will produce hydrogen, like before. CO2 and hydrogen are fed into a Sabatier reactor, which uses high temperatures, pressure and catalysts to produce methane. Methane is the main component of natural gas, which means we can use the conventional gas grid to store it. We transport the methane to the nearest gas injection point, which is denoted by the green dot, and inject it into the gas grid. When we need power, we can use existing gas turbines to regenerate the power. Now here's the challenge. When regenerating power in gas turbines, we emit CO2 into the air. In order to create a truly sustainable and circular system, we therefore need to capture 100% of the emitted CO2 and reuse it, or we need to use CO2 captured from air. While these technologies are developing fast, truly sustainable CO2 capture is still a challenge. Now, simulation of these systems shows several challenges we have to face. The first challenge is CapEx efficiency. Because we are using expensive equipment, we want to make efficient use of the system to reach our return of investment in time. However, in a flexible storage system, the CapEx-intensive system only operates part of the time, which means we have high investment costs and a very long return on investment time. The levelized cost of storage will therefore go up. The second challenge is ramp up, ramp down. The primary goal of the storage system is to provide flexibility for the electricity grid. However, quick ramp up and ramp down are difficult with high temperature, high pressure reactors. Ramping up and down too frequently will affect the efficiency and the lifetime of your equipment. In addition, not all reactors are currently designed to do this, so not all can be switched off and on within short periods of time. Then there's the cost. Many of the components are relatively expensive, especially the electrolyzer. The simulation shows a cost of storage of at least 26 eurocents per kilowatt hour to be added to the current electricity price. This means energy prices will be close to unaffordable in the future. Another challenge is the round-trip efficiency. Each step of conversion and transport has an impact on the efficiency. The round-trip efficiency of these systems is around 35%, which means we lose a lot of the energy that we've produced. While the electricity was originally in excess, an inefficient storage system means a strong increase in the required surface area for solar and wind to still provide enough energy in energy-scarce periods. One of the more technology-driven challenges that we're facing is the scale-up. Fuel cells, electrolyzers, and reactors exist, but they are currently not large enough to store energy for a 1 gigawatt wind park. A 1 gigawatt wind park, for example, would need a 450 megawatt electrolyzer to use all excess energy. This system size has not been created so far. And finally, an interesting challenge is the availability of inputs. For example, CO2 capture from air is a challenge, and you can imagine in some countries purified water is difficult to come by. This challenge is often overlooked, but will become more and more important as climate change causes more serious water scarcity issues. All in all, there are quite a lot of challenges we face in the implementation of Power-to-X-to-Power. Now let's recap. Power-to-X-to-Power is an alternative energy storage technology, specifically for large-scale energy storage. We need Power-to-X-to-Power because the existing capacity of energy storage is very low. We don't have the alternatives yet. The system design differs strongly between the molecules. We've seen the systems for hydrogen, methane, and ammonia. Also, we've seen the challenges Power-to-X-to-Power faces. They are CapEx efficiency, flexibility, cost, efficiency, scaling, and input availability. The conclusion I would like to draw is Power-to-X-to-Power, we can't live with it, and we can't live without it. Thank you very much, and I look forward to seeing you in the assignments.